On September 14th, 2015, humanity heard something impossible. We detected a sound that had been traveling across the cosmos for 1.3 billion years, originating from an event of unimaginable violence. But this sound didn't travel through a medium like air or water. It was a sound that had no medium, because it was a vibration of space-time itself. For the first time, we didn't just see the universe, we heard it. And the sound we heard was the thunderous final chirp of two black holes, each 30 times the mass of our Sun, smashing together and becoming one. It was the sound the universe makes when its most extreme objects collide.
To understand this cosmic sound, you first have to unlearn what you know about sound itself. The familiar sounds of your world are pressure waves traveling through a substance, like air. Space is a near-perfect vacuum, which is why it's often called silent. But this silence is only part of the story. Albert Einstein, in his general theory of relativity, imagined the universe as a four-dimensional fabric called space-time. He predicted that massive objects walked this fabric like a bowling ball on a trampoline. He also predicted that when these massive objects accelerate, they should create ripples in the fabric, much like flailing your arms in a pond creates waves. These ripples are gravitational waves, and they are what we can now hear.
The source of the first sound we ever heard was a spectacular cosmic dance. Imagine two black holes born from the collapse of ancient, massive stars locked in a gravitational embrace. For millions of years, they orbited each other in a slow, graceful spiral. But with every orbit, they radiated away a tiny amount of energy in the form of these gravitational waves. This loss of energy acted like a brake, causing their orbit to decay, pulling them closer and closer together. As they got closer, their speed increased dramatically, and the frequency of the gravitational waves they emitted began to rise. They were a cosmic instrument, spinning up from a low bass hum into a final, rising tone. In the final fraction of a second, the dance became a frenzy. The two black holes, now separated by only a few hundred kilometers, were whipping around each other at more than half the speed of light. The space-time around them was being distorted into a violent, churning storm. And then they touched. Their event horizons merged, and in an instant of cosmic annihilation, they coalesced into a single, larger black hole. In that moment of merger, an amount of energy equivalent to 3 times the entire mass of our Sun was converted not into light, not into heat, but into a pure, catastrophic blast of gravitational waves, a tsunami of space-time that began its long journey outward in all directions. For 1.3 billion years, this ripple of space-time traveled unimpeded through the cosmos. It passed through countless galaxies, interstellar dust clouds, and star systems. Unlike light, which can be absorbed, scattered, or blocked, gravitational waves interact very weakly with matter. They are the ultimate cosmic messengers, carrying a pure and unaltered story of their violent origin. This specific wave traveled from a distant, unnamed galaxy, crossed the vast intergalactic void, entered our own Milky Way, passed through our solar system, and on that September morning in 2015, it washed over the Earth, stretching and squeezing the very planet we stand on. The change was infinitesimal, a distortion thousands of times smaller than the nucleus of a single atom. Detecting it required one of the most sensitive scientific instruments ever built. LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO consists of two identical facilities, thousands of kilometers apart. Each one is a giant L-shaped detector with two 4-kilometer-long arms held in a near-perfect vacuum. A powerful laser is split, with one beam sent down each arm. These beams reflect off hyper-polished mirrors and return to the source. Under normal conditions, the returning light waves are perfectly aligned to cancel each other out, producing darkness. But when a gravitational wave passes, it minutely stretches one arm while squeezing the other, knocking the lasers out of sync and allowing a flicker of light to escape to the detector.
That flicker of light is the signal. It's a waveform, a graph showing how the fabric of space-time stretched and compressed over time. For the black hole merger, the waveform showed a signal that rapidly increased in both frequency and amplitude before abruptly stopping. Scientists can take this data, this raw vibration of space-time, and translate it into the range of human hearing. The famous chirp sound is not an artistic interpretation. It is a direct audio transcoding of the gravitational wave. You are literally listening to the frequency of space-time changing as these two black holes spiraled into their doom. It is the purest sound in the universe.
But the signal didn't just stop. After the main chirp of the merger, there was a final crucial component, the ringdown. The new combined black hole that was born from the collision was initially misshapen, wobbling violently like a bell that has just been struck. To settle into its final, perfect spherical state, it had to radiate away this excess energy as a final burst of gravitational waves. The precise pitch and decay of this ringdown are predicted exactly by Einstein's equations, and they depend only on the final black hole's mass and spin. Hearing that ringdown was the ultimate confirmation. It was the universe singing in perfect harmony with a theory devised a century earlier by a man with nothing more than a pen, paper, and his own magnificent imagination.
The detection of GW 150914 was more than just a Nobel Prize-winning discovery. It was the birth of a completely new way to experience the cosmos. For all of human history, our understanding of the universe has come from observing electromagnetic radiation, visible light, radio waves, X-rays. We have been watching a silent movie. But gravitational waves have given us a new sense. We can now listen to the universe's most dramatic and hidden events. We can hear the collision of black holes, the merger of neutron stars, and perhaps one day the echoes of the Big Bang itself. This is the dawn of gravitational wave astronomy, a new era that will allow us to map the dark, unseen side of the universe.
That chirp, a sound that lasted less than a second, was the universe whispering one of its most profound secrets. It was a message that traveled for a third of the age of life on Earth, finally received by an instrument of incredible human ingenuity. It confirms that the stage upon which the cosmic drama unfolds, space-time itself, is not static, but a dynamic and vibrant entity that can be made to ring and sing. The sound of two black holes colliding is the ultimate demonstration of Einstein's genius and a testament to our own relentless curiosity. We are no longer just looking at the stars,
We are now listening to their symphony, feeling the very rhythm of the cosmos itself.